What if everything you know about Earth is a lie? What if our perfect planet, sitting in the exact right spot, with the exact right conditions for life, isn't a cosmic accident, but a carefully designed experiment? Right now, as you're watching this video, you might be part of the most elaborate scientific study ever conducted, and you don't even know it. Today, we're diving deep into evidence that suggests our entire world might be nothing more than a laboratory. Our lives, nothing more than data points in someone else's research. From impossible statistical coincidences to mysterious gaps in physics that seem deliberately placed, the clues are everywhere once you know where to look. If you're ready to question everything you thought you knew about reality, make sure to subscribe to the Lazy Cosmos for more mind-bending explorations of our universe's deepest mysteries. Trust me, after what you're about to discover, you'll never look at Earth the same way again. Let's begin. Let's begin with a truth so startling, so mathematically improbable, that it becomes almost impossible to ignore. Earth is perfectly, almost suspiciously, balanced between chaos and calm. Just the right temperature, just the right distance, just enough time. This is the famous Goldilocks paradox, a term borrowed from the children's fairy tale. But in this case, it's a mystery that feels written by the universe itself. Imagine floating above our planet, not just hundreds of miles up, but at the very edge of sight. So Earth appears as a blue marble, a shimmering sphere suspended in shadow. At first glance, it's just one more world circling an average star. But blink, and the surface glows with oceans. Endless water, swirling clouds, traces of green and gold, taut energy and flashes of lightning. Yet what's truly extraordinary is not its appearance, but its location in the cosmic theater. Earth, you see, resides in a place astrobiologists call the habitable zone. It's a thin ring surrounding any star where the conditions are not too hot, not too cold, but just right for liquid water, a fundamental ingredient for life as we know it. When you look at the vastness of the galaxy, you see billions of stars, each perhaps with their own planets. But only a narrow band around each star fits this Goldilocks description. Too close, and heat vaporizes water, cooking seas to clouds and burning the surface sterile. Too far, and everything freezes, locked in eternal, icy stillness. But with Earth, it's not just about the zone, it's about the margins. The margin for error is razor thin, a nudge that seems trivial on a galactic scale, moving just a few percent closer or farther from the sun, could spell doom for every living thing. If our planet were only 5% nearer the solar inferno, temperatures would soar, transforming gentle rains into endless steams, rivers into boiling, hostile moats, lush forests into withered husks. We would become Venus, a world where metallic lead melts in the open, where air is thicker than water, and not a drop of liquid could last. But if Earth drifted just 5% farther from the sun, the transformation would be even more chilling. Our blue planet would become a frozen wilderness, much like Mars, where ancient riverbeds and canyon scars hint at water, but the present is only dust and frost. Those tight constraints alone are enough to spark wonder and, perhaps, suspicion. Yet, astonishingly, there's more. Because the sun itself is not constant. It pulsates, flares, and occasionally lashes out with tempestuous solar winds. Earth's orbit is not perfectly circular, but a gentle oval, ensuring our planet never strays too far from its life-sustaining warmth, yet never falls prey to its fury. And then, there's our atmosphere. Earth's shimmering, invisible shield does more than hold in the soft oxygen breeze of dawn or cradle the sounds of living things. It performs a delicate balancing act, letting in just enough sunlight to nurture forests and spark photosynthesis, but reflecting or absorbing the rest so that our world doesn't cook or freeze. If our atmosphere were much thicker, as on Venus, sunlight would become a prison, trapped to build relentless heat. If it were thinner, like frigid Mars, the breath that carried our ancestors would simply slip away, fading into cosmic silence. So much rests on chance, and yet the chances are so remote, they beggar belief. The composition of our air, 78% nitrogen, 21% oxygen, trace gases making up the remainder, seems as though measured by a cosmic chemist's hand. Tilt the balance just a little, and our world transforms. Increase the oxygen just slightly, and lightning would set forests ablaze more often than rain could quench them. Lower it, and complex life would suffocate before it could even begin. But we're only at the beginning of the oddities. Now let's talk about our moon. Sleepy, silent, reflecting silver light across midnight oceans, the moon has guarded our night for eons. Yet its role is far more profound and suspicious than mere decoration. The moon is almost exactly 1/4 the diameter of the Earth, an outrageous size compared to other planetary moons. Most other planets, if they have moons at all, are attended by rocky pebbles, lumpy spheres, or distant satellites tiny in comparison. But not Earth. Our companion hovers close enough and is large enough to wield astonishing gravitational influence. It's the moon's pull that creates the tides, drawing the oceans back and forth, stirring the shallow coasts, flooding tidal pools with every rising wave. In those tidal zones, neither holy sea nor holy land, life first crawled out of water, taking the leap that transformed simple cells into complex beings millions of years ago. But the moon does more than stir water. It acts as a planetary anchor, stabilizing our planet's tilt. That tilt, known formally as axial tilt, is what gives us seasons. Without the moon's gravitational embrace, Earth's tilt would lurch chaotically, sometimes swinging by tens of degrees, flipping climates in the span of centuries. Imagine the chaos. Tropical forests frozen by polar winds, ice caps melting into primal jungles, weather systems so volatile no complex life could endure. Stability is survival, and the moon gifts us that in abundance. Even the circumstances of the moon's birth sound almost scripted. The most accepted theory, aptly called the giant impact hypothesis, holds that billions of years ago, a Mars-sized object, Theia, slammed into the infant Earth. The resulting cataclysm ejected molten rock into orbit, which coalesced into our satellite. The odds of this happening, in the precise way, needed to create both a large moon and a stable planetary axis, are almost laughably small. And yet, it did. Or did it? The more closely scientists look, the more the fine details of the moon's composition and orbit strain against accepted explanation. Still, let's not forget about our magnetic field, another crucial piece of this planetary puzzle. Generated deep within Earth's molten iron core, it wraps the planet in an invisible force, a cocoon that shields us from solar and cosmic radiation. Mars, once boasting a magnetic field, lost it, and with it, any hope for a stable atmosphere. But our field remains, fluctuating and even flipping every few 100,000 years, but always returning before lasting harm is done. That field isn't just luck. It depends on the size of our planet. larger, and the core would cool too slowly to generate enough dynamo action. Smaller, and the core would have solidified eons ago, robbing us of protection. On Earth, the fit is exact. Even the dance of the continents, known as plate tectonics, plays its part. Only a handful of planets show evidence of active tectonics, and without it, essential elements would remain locked away in rocks, never to cycle into oceans or air. Volcanoes release trapped gases, renewing life's palette. Earthquakes churn minerals to the surface, feeding ancient bacteria who transform the world. The engine of geology, powered by the relentless tug between crust and core, has sustained the balance of air and ocean since life's first flickering spark. Here's what all this adds up to: a planet in a galaxy teeming with deadly, barren worlds, where not one, not two, but a dozen or more independent parameters must be just so for life to even stand a chance. Our distance from the sun, the chemistry of our atmosphere, the tilt of our axis, the presence, size, and position of our moon, the churning heart of our core, the restless plates upon which our mountains rise and fall, the stable temperatures, mild seasons, gentle rains. Remove or alter any one of these, and Earth's gentle cradle becomes a coffin. Some might say, well, it simply had to be this way for us to be here at all. That's the anthropic principle, and on the surface, it sounds convincing. But when you start adding up the probabilities, it feels less like rolling a die and more like flipping a coin 100 times and landing on heads every single time. Is it random chance, or have we stumbled onto evidence of something deeper? Is our planet really just lucky? Or is the luck itself a sign that our world was selected, prepared, and nurtured for some unknown purpose? Even the notion of what is ordinary or rare becomes suspect. Astronomers scan the skies, mapping distant exoplanets in hopes of finding another world with a familiar signature. So far, in the glittering expanse, thousands of alien worlds have been cataloged, but almost none resemble Earth in their exact ratios, their mysterious balances, their unflappable calm. So tonight, as you listen and drift into the gentle quiet of midnight, ask yourself, is it really likely that all these coincidences, dozens of them, all working together, just happen to make the only blue planet we've found so far in an ocean of black space? Or is it something more? Something planned? Something watched? In the Goldilocks paradox, maybe the greatest mystery is not why we are here, but who or what decided that we should be. Let these thoughts fade with the rhythm of your breath, the heartbeat of your world, as you close your eyes and float in the gentle cradle this universe has made. Too perfect, perhaps, to be a simple accident. Now let's venture deeper into the cosmic mystery, beyond Earth's perfect positioning and into the very fabric of reality itself. Here, in the invisible architecture that governs every atom, every star, every force that shapes the universe, we discover something far more unsettling than even our planet's suspicious perfection. We find that the entire cosmos appears to have been calibrated with a precision so exacting, so mathematically improbable, that it challenges every assumption we hold about randomness and natural selection. This is the fine-tuning mystery, a riddle written in the language of physics itself. Imagine holding the universe in your hands like an impossibly complex instrument with dozens of dials and controls that must be set to precise values for anything: stars, planets, atoms, life, to exist at all. Each dial represents a fundamental constant, a basic rule that governs how reality operates: the strength of gravity, the power of electromagnetic forces, the binding energy that holds atomic nuclei together, the rate at which the universe expands. Turn any dial just slightly in the wrong direction, and existence itself collapses into meaninglessness. Let's begin with perhaps the most staggering example: the cosmological constant, a number that determines how rapidly our universe expands. This single parameter must be tuned to a precision that defies comprehension, accurate to 1 part in 10 to the power of 120. To grasp this level of precision, imagine trying to hit a target the size of a single atom. But the target is located somewhere within a sphere the size of the entire observable universe. Miss by even the tiniest fraction, and the consequences are absolute. If the cosmological constant were just slightly larger, space itself would expand so rapidly that matter could never clump together to form galaxies, stars, or planets. The universe would become a cold, empty void, expanding forever into nothingness. If it were smaller, gravity would overwhelm the expansion, causing the cosmos to collapse back on itself in a reverse Big Bang before stars could even begin to shine. But this is only the beginning. Consider gravity itself, that invisible force that keeps planets in orbit, that shapes galaxies, that allows stars to burn in nuclear fusion. Gravity is remarkably weak compared to other forces. The electromagnetic force that holds electrons in atoms is trillions upon trillions of times stronger than gravity. Yet if gravity were just 1% stronger, stellar evolution would accelerate catastrophically. Stars would burn through their nuclear fuel so quickly that complex life would have no time to evolve. Planets would be pulled into their stars or crushed under their own weight. If gravity were 1% weaker, matter would never clump together at all. Gas clouds would drift apart before they could collapse to form stars. Without stars, there would be no nuclear furnaces to create the heavy elements essential for life: carbon, oxygen, nitrogen, iron. The universe would remain forever a thin soup of hydrogen and helium, cold and lifeless. Then there's the strong nuclear force, the invisible glue that binds protons and neutrons together in atomic nuclei. This force operates only at incredibly short distances, smaller than the nucleus of an atom. But its strength must be calibrated with extraordinary precision. If the strong force were just 2% weaker, protons and neutrons could not bind together. Atomic nuclei would fly apart, and the universe would contain nothing but hydrogen, single protons with no possibility of forming heavier elements. There could be no carbon, no oxygen, no chemistry complex enough to build molecules, proteins, or DNA. If the strong force were 2% stronger, protons would bind so tightly that hydrogen itself could not exist. All protons would fuse immediately into heavier elements, and there would be no fuel for the long-burning stars that provide stable energy for billions of years. The electromagnetic force presents its own delicate balance. This is the force that governs how electrons orbit atomic nuclei, how atoms bond to form molecules, how light travels through space. If electromagnetic force were slightly stronger, electrons would spiral into atomic nuclei, atoms would become impossibly small and dense, and chemistry as we know it could not exist. If it were weaker, electrons would drift too far from nuclei, atoms would be enormous and unstable, and again, complex molecules could never form. Even more mysterious is the fine structure constant, a dimensionless number that characterizes the strength of electromagnetic interactions between particles. This constant, approximately equal to 1 divided by 137, appears throughout the equations of quantum mechanics and relativity. Small changes to this number would alter the energy levels of atoms, making stellar nucleosynthesis, the process by which stars create heavy elements, impossible. Stars would either burn too hot and die too young, or burn too cool to forge the elements necessary for rocky planets and biological chemistry. The weak nuclear force, responsible for certain types of radioactive decay and nuclear reactions, must also be precisely tuned. If it were much stronger, the nuclear reactions that occurred in the first few minutes after the Big Bang would have converted all hydrogen into heavier elements. Without hydrogen, there could be no water, no long-lived stars, no chemical processes that depend on this simplest and most abundant element. If the weak force were much weaker, these same nuclear reactions would have produced almost no heavy elements at all, leaving the universe with insufficient raw materials for planets and life. Perhaps most troubling of all is the ratio between the masses of fundamental particles: electrons, protons, neutrons. The mass of an electron compared to a proton is approximately 1 to 1,836. This ratio determines the size of atoms, the strength of chemical bonds, the stability of matter itself. Change this ratio by even a small amount, and atoms become either too large or too small to form stable molecules. The delicate dance of chemistry that allows carbon-based life requires this ratio to fall within an incredibly narrow range. The neutron is just slightly heavier than the proton, by about 0.1%. This tiny mass difference determines whether neutrons can exist outside atomic nuclei, whether they decay into protons and electrons, and whether the nuclear reactions inside stars can proceed normally. If neutrons were much lighter, they would be stable outside nuclei, and all protons would convert to neutrons, eliminating hydrogen and making stars impossible. If neutrons were much heavier, they would decay too quickly inside atomic nuclei, making all elements except hydrogen unstable. Consider also the rate at which the universe has expanded since the Big Bang. This expansion rate is determined by the total amount of matter and energy in the cosmos, and it must fall within a precise range for galaxies and stars to form. If the universe had expanded too quickly, matter would have been spread too thin for gravitational clumping to occur. If it had expanded too slowly, everything would have collapsed back into a singularity before stars could ignite. The observed expansion rate sits perfectly in the narrow window that allows for billions of years of stable cosmic evolution. The amount of ordinary matter compared to dark matter and dark energy also appears to be fine-tuned. Dark matter provides the gravitational scaffolding that allows galaxies to form. But if there were too much, galaxies would collapse into black holes. If there were too little, galaxies would never condense out of the primordial gas clouds. The ratio of ordinary matter to dark matter must be calibrated to allow for the formation of structure on galactic scales while still permitting the formation of stars and planets on smaller scales. Even the number of spatial dimensions in our universe appears to be fine-tuned for complexity. In a universe with only 2 spatial dimensions, complex networks, like neural systems, could not exist. Gravity would not follow an inverse square law, making stable planetary orbits impossible. In a universe with 4 or more spatial dimensions, atoms would be unstable. Electrons would spiral into nuclei, and again, chemistry could not proceed. Three spatial dimensions appear to be the minimum required for complex structures and the maximum that allows for stable matter. What makes this fine-tuning so deeply mysterious is that these constants appear to have no physical reason for their specific values. They are not determined by more fundamental principles. They simply are what they are, as if someone had carefully adjusted the settings on a cosmic control panel before the universe began. The mathematical probability of all these parameters falling within their life-permitting ranges by pure chance is so astronomically small that it approaches zero. Some physicists have calculated that the odds of our universe having the precise combination of constants necessary for life are comparable to the probability of throwing a dart from Earth and hitting a target the size of a coin somewhere on the surface of a planet orbiting a star in a distant galaxy. Others suggest the probability is even smaller, like hitting a target the size of a single atom located somewhere in the observable universe. This extraordinary fine-tuning forces us to confront an uncomfortable question. Are we witnessing the result of countless random universes, where only the rare few with the right constants develop observers who can notice their good fortune? Or are we seeing evidence of intentional calibration, a universe designed and tuned by some intelligence vast enough to comprehend the intricate relationships between dozens of interconnected parameters? The silence of the cosmos adds another layer to this mystery. In a universe fine-tuned for life, where billions of planets circle billions of stars in billions of galaxies, why do we find ourselves apparently alone? Why have we detected no signals, no evidence, no trace of other civilizations that should have emerged in such a life-friendly cosmos? Perhaps the fine-tuning itself provides a clue. Maybe these precise settings don't just allow life to develop, but are specifically calibrated for one particular experiment, one particular world, one particular biosphere. As you drift towards sleep tonight, let these numbers wash over you like waves of possibility. Somewhere in the architecture of reality, in forces too small to see and too vast to comprehend, the universe reveals a pattern of precision that makes our existence seem less like an accident and more like a carefully orchestrated symphony. In the gentle rhythm of your breathing, in the electrical firing of neurons in your brain, in the nuclear fusion of distant stars that forge the elements in your body, the fine-tuned constants of physics continue their ancient work, maintaining the delicate balance that allows consciousness itself to contemplate these deepest mysteries of existence. If the fine-tuning of fundamental constants feels unsettling, what we're about to explore ventures into territory that's even more mysterious. Beyond the precisely calibrated dials of physics lie deeper layers of cosmic arrangement, patterns, and relationships that seem to transcend mere numerical coincidence. Here, we discover that the universe's apparent design extends far beyond individual parameters and into the very structure of reality itself, revealing a web of interconnected phenomena that challenges our most basic assumptions about how existence came to be. Let's begin with something that might initially seem mundane, but becomes extraordinary under closer examination: the precise relationship between particle masses. The electron, that fundamental building block of atoms, has a mass that is exactly 1/1836 the mass of a proton. This isn't approximately that ratio. It's precisely that ratio, measured to extraordinary decimal places. Change this relationship by even a fraction of a percent, and the entire architecture of matter collapses. Atoms would be either too large to bond into molecules or too small to maintain stable configurations. The delicate dance of chemistry that allows carbon to form 4 bonds, oxygen to form 2, and hydrogen to form 1, the very basis of organic molecules, depends entirely on this exact mass ratio. But here's what makes this even more mysterious. There's no known physical principle that demands this particular ratio. The masses of fundamental particles appear to be what physicists call brute facts. They simply are what they are, with no deeper explanation for their specific values. Yet somehow, out of an infinite range of possible masses, these particles emerge from the Big Bang with exactly the right weights to allow complex chemistry to unfold over billions of years. Consider the neutron, slightly heavier than the proton by just 0.14% of the proton's mass. This tiny difference determines whether neutrons can exist outside atomic nuclei, and it governs the nuclear reactions that occur in the cores of stars. If neutrons were lighter than protons, all protons would decay into neutrons, eliminating hydrogen from the universe and making long-lived stars impossible. If neutrons were significantly heavier, they would decay too quickly inside atomic nuclei, making all elements except hydrogen unstable. The neutron's mass sits in a narrow window that allows for both stable hydrogen and stable heavy elements, a coincidence so precise it's measured in fractions of electron volts out of masses measured in hundreds of millions of electron volts. The relationships between forces reveal even deeper mysteries. The electromagnetic force that holds electrons in atoms is precisely 137 times weaker than it could theoretically be, a ratio embedded in what physicists call the fine structure constant. This number, approximately 137, appears throughout quantum mechanics and relativity theory, yet no one knows why it has this specific value. Richard Feynman, one of the greatest physicists of the 20th century, called it one of the greatest damn mysteries of physics, and suggested that all good theoretical physicists should worry about this number. Small changes to this constant would alter the energy levels of atoms, making the nuclear reactions inside stars either impossible or catastrophically violent. The carbon-12 nucleus provides perhaps the most famous example of what seems like cosmic fine-tuning for life. Carbon is essential for all known forms of life, but creating carbon in stellar cores requires a nuclear reaction so improbable it should barely happen at all. 3 helium nuclei must collide and fuse almost simultaneously, a process called the triple alpha reaction. Fred Hoyle, the brilliant astronomer who first worked out this process, realized that unless carbon-12 had a very specific energy level, these reactions would be far too rare to explain the abundance of carbon we observe in the universe. When experimenters looked for this predicted energy level, they found it exactly where Hoyle said it should be. A discovery that led Hoyle himself to comment that a super intellect has monkeyed with physics. But the carbon coincidence extends even further. Not only must carbon-12 have the right energy level to form easily, it must also have exactly the right properties to avoid being immediately destroyed. If carbon nuclei were just slightly more reactive, they would combine with helium to form oxygen before they could accumulate in significant quantities. The energy levels of both carbon and oxygen nuclei appear to be perfectly balanced to allow carbon production while preventing carbon destruction. A double coincidence that strains credibility. The expansion rate of the universe presents another layer of mysterious precision. Space itself has been expanding since the Big Bang, but the rate of this expansion must fall within incredibly narrow limits for galaxies and stars to form. If the universe had expanded just slightly faster in its early moments, matter would have spread out too quickly for gravitational attraction to pull gas clouds together into the dense regions that eventually became stars. If it had expanded slightly slower, gravity would have overwhelmed the expansion, causing the entire universe to collapse back on itself long before the first stars could ignite. The observed expansion rate sits precisely in the narrow band that allows for billions of years of stable cosmic evolution. This expansion is governed by the total amount of matter and energy in the universe, including mysterious dark matter and dark energy that we can detect but don't understand. Dark matter, which outweighs ordinary matter by a factor of 5 to 1, provides the gravitational scaffolding that allows galaxies to form. Too much dark matter, and galaxies would collapse into massive black holes. Too little, and galaxies would never condense from the primordial gas. The ratio appears to be calibrated for maximum cosmic complexity, allowing structures to form on scales from planets to galaxy clusters while maintaining stability over billions of years. Dark energy, which drives the accelerating expansion of space itself, presents an even greater mystery. This invisible force comprises about 70% of all energy in the universe, yet its strength appears to be fine-tuned to extraordinary precision. If dark energy were slightly stronger, it would have prevented the formation of galaxies by accelerating cosmic expansion too rapidly. If it were slightly weaker, the universe might already have begun collapsing under its own gravity. The observed strength of dark energy allows for a universe that forms complex structures but continues expanding for hundreds of billions of years, providing ample time for life to evolve and civilizations to develop. The dimension of space itself appears to be fine-tuned for complexity. Our universe has exactly 3 spatial dimensions plus 1 time dimension, but mathematics allows for universes with different dimensional structures. In a universe with only 2 spatial dimensions, complex networks like neural systems couldn't exist. There wouldn't be enough room for the intricate connections required for consciousness. Gravity wouldn't follow an inverse square law, making stable planetary orbits impossible. In a universe with 4 or more spatial dimensions, atoms would be unstable. Electrons couldn't maintain stable orbits around nuclei, and chemistry as we know it couldn't exist. 3 dimensions appear to be the minimum necessary for complexity and the maximum compatible with stable matter. Even more subtle is the way different physical forces complement each other to create stable, long-lived structures. Electromagnetic forces hold atoms and molecules together, but they must be balanced against thermal motion to allow chemical reactions without causing everything to fly apart. Gravitational forces must be strong enough to hold planets and stars together, but weak enough not to crush complex structures. The nuclear forces must be calibrated to allow both hydrogen fusion in stellar cores and the existence of heavy elements in planetary crusts. Each force operates in its own domain, yet somehow they're all tuned to work together in creating a universe where matter can organize into increasingly complex patterns over cosmic time. The nuclear processes that created the elements essential for life required a sequence of coincidences spanning billions of years. First-generation stars had to burn hydrogen into helium, then fuse helium into carbon, oxygen, and heavier elements. These massive stars had to explode as supernovas to scatter their newly created elements into space. Second-generation stars had to form from this enriched material, creating planetary systems with rocky worlds containing the chemical diversity necessary for biology. The nuclear reaction rates, stellar evolution timescales, and galactic mixing processes all had to be coordinated to produce planets with the right mixture of elements at the right time in cosmic history. Perhaps most mysterious of all is the initial state of the universe itself. Mathematical physicist Roger Penrose has calculated that the probability of our universe beginning in a low entropy state, organized enough to allow the development of complex structures, is approximately 1 in 10, to the power of 10 to the power of 123. This is a number so large that if you wrote it out, it would contain more digits than there are particles in the observable universe. Yet somehow, our cosmos began in exactly this improbable configuration, with just enough organization to allow galaxies, stars, planets, and life to emerge, but not so much organization that everything immediately crystallized into a static, changeless state. The convergence of all these factors, particle masses, force strengths, expansion rates, dimensional structure, initial conditions, creates a picture of a universe that seems almost impossibly well suited for the development of complexity and consciousness. Each parameter appears to be set not just within the range that allows some form of matter to exist, but within the much narrower range that allows for the emergence of chemistry, geology, biology, and ultimately thinking beings capable of contemplating their own existence. As you settle into the quiet rhythm of evening, let these deeper mysteries wash through your consciousness like gentle waves of wonder. In the spaces between atoms, in the silent dance of forces too subtle to feel, in the vast choreography of cosmic evolution, the universe reveals layer upon layer of apparent intention. Whether this reflects conscious design or represents the outcome of processes beyond our current understanding, the fine-tuning of reality extends far beyond simple numerical coincidences into the very fabric of existence itself. Close your eyes and drift with the knowledge that you are embedded in a cosmos whose every parameter seems calibrated for the miracle of your own awareness, a mystery as profound as it is beautiful. As we venture deeper into the mystery of our universe's apparent design, we encounter something that transcends even the fine-tuning of individual constants. What we discover is a vast, interconnected hierarchy of cosmic balance, layers upon layers of precisely orchestrated relationships that must all work in harmony for existence itself to unfold. This is where the mystery becomes truly profound, where the mathematical improbabilities stack upon each other like an endless tower of coincidences, each one necessary, each one seemingly impossible, yet all somehow perfectly coordinated in the grand symphony of reality. Imagine the universe as a vast musical instrument with billions of strings that must all be tuned to precise frequencies to create harmony rather than chaos. Each string represents a different aspect of physical reality, not just the fundamental constants we've explored, but the complex relationships between them, the way they influence each other across vast scales of space and time, and how they collectively orchestrate the emergence of structure and complexity. What we find is that these cosmic strings are not just individually tuned, but tuned in relation to each other with a precision that defies all reasonable expectation of chance. Let's begin. with the extraordinary relationship between the electromagnetic force and gravity as they govern the behavior of stars. The electromagnetic force determines how atoms interact and how electrons move within matter, while gravity determines how masses attract each other across cosmic distances. These two forces operate on completely different scales and through entirely different mechanisms, yet their relative strengths must be balanced with incredible precision to allow stars like our Sun to exist and shine steadily for billions of years. If the electromagnetic force were slightly weaker relative to gravity, electrons would be pulled closer to atomic nuclei, making atoms smaller and denser. This would affect the opacity of stellar material, how easily light can pass through the hot gas inside stars. With reduced opacity, radiation would escape more easily from stellar cores, cooling them and slowing nuclear fusion reactions. Stars would burn dimmer and cooler, becoming red dwarfs that produce too little energy to support photosynthesis on nearby planets. The habitable zones around such stars would be so close that planets would become tidally locked, with one side permanently facing the star and the other in eternal darkness. Conversely, if the electromagnetic force were slightly stronger relative to gravity, the opposite would occur. Atoms would become larger and less dense, stellar material would become more opaque, and radiation would be trapped more effectively within stellar cores. This would cause stars to burn hotter and faster, becoming blue giants that consume their nuclear fuel in mere millions of years rather than billions. Such stars would also emit dangerous levels of ultraviolet and X-ray radiation, sterilizing any nearby planets before life could gain a foothold. The balance point between these extremes, where stars can burn steadily at moderate temperatures for billions of years, occupies an extraordinarily narrow range in the possible values of these fundamental forces. Yet somehow, our universe sits precisely in this narrow window, allowing for the existence of stable, long-lived stars that can nurture the slow processes of planetary evolution and biological development. This stellar fine-tuning connects to an even deeper mystery involving the nuclear forces that govern reactions in stellar cores. The strong nuclear force must be precisely calibrated not just to hold atomic nuclei together, but to allow the specific sequence of nuclear reactions that creates the elements essential for life. In the cores of massive stars, helium nuclei must fuse together in the triple alpha process to create carbon. But this reaction is so improbable, it almost doesn't happen at all. 3 helium nuclei must collide almost simultaneously, and they must do so in a way that creates a carbon nucleus in exactly the right quantum state to avoid immediately breaking apart. The energy levels of carbon and oxygen nuclei appear to be perfectly tuned to make this process work. Carbon-12 has a specific energy level that makes its formation just likely enough to explain the abundance of carbon we observe in the universe, while oxygen-16 has energy levels that prevent it from destroying carbon as quickly as carbon is created. This double coincidence, known as the Hoyle resonance after astronomer Fred Hoyle, who predicted it, seems almost impossibly convenient. Change the strong nuclear force by just a few percent, and either no carbon would be produced, or all carbon would be immediately converted to oxygen, leaving the universe without the element that forms the backbone of all organic chemistry. But the hierarchy of fine-tuning extends far beyond individual nuclear reactions to encompass the entire life cycle of cosmic evolution. The rate at which the universe expanded in its earliest moments had to be precisely calibrated to allow matter to clump together into galaxies and stars, but not so slowly that everything would collapse back into a primordial black hole. This expansion rate is determined by the total energy density of the universe, including contributions from ordinary matter, dark matter, and the mysterious dark energy that drives accelerating expansion. Dark matter, which comprises about 27% of the universe's total energy, provides the gravitational scaffolding that allows galaxies to form. Without dark matter, ordinary matter would be spread too thinly through space for gravity to pull it together into the dense regions where stars are born. Too much dark matter, however, and galaxies would collapse into massive black holes before stars could form and begin producing heavy elements. The observed ratio of dark matter to ordinary matter appears to be calibrated for maximum cosmic productivity, allowing galaxies to form and maintain their structure while still permitting the formation of individual stars and planetary systems. Dark energy presents an even more dramatic example of cosmic fine-tuning. This invisible force, which comprises about 73% of the universe's energy budget, drives the accelerating expansion of space itself. The strength of dark energy appears to be tuned to a precision that staggers the imagination, accurate to approximately 1 part in 10 to the 120. This number is so large that if you wrote out all its digits, the resulting string of numbers would contain more characters than there are atoms in the observable universe. If dark energy were even slightly stronger, it would have prevented the formation of galaxies by accelerating cosmic expansion too rapidly in the early universe. Gas clouds would have been stretched apart before they could collapse under their own gravity to form the first generation of stars. If dark energy were slightly weaker, its effects would be overwhelmed by gravity, and the universe might already have begun contracting, heading toward a big crunch that would destroy all complex structures. The observed strength of dark energy allows for a universe that forms galaxies and stars, but continues expanding for hundreds of billions of years, providing vast stretches of time for evolution and the development of complexity. The precision required for this dark energy tuning is so extreme that it represents what physicists call the worst fine-tuning problem in physics. There is no known physical principle that explains why dark energy should have this particular strength rather than being either zero or enormously larger. Yet somehow, out of an effectively infinite range of possible values, dark energy emerged with exactly the strength needed to create a long-lived, structure-rich universe. Even the initial conditions of the universe itself appear to be fine-tuned with extraordinary precision. Mathematical physicist Roger Penrose has calculated that the probability of the universe beginning in a low-entropy state, organized enough to allow the development of complex structures over billions of years, is approximately 1 in 10. 10 11 23. This is a number so vast that it cannot be comprehended in ordinary terms. To put it in perspective, if you could examine every possible way of arranging all the particles in the observable universe, and each arrangement took 1 second to examine, it would take longer than the age of the universe multiplied by itself, billions upon billions of times, to examine even a tiny fraction of the possible arrangements represented by this probability. Yet somehow, our universe began in exactly this improbable low-entropy configuration. It started with just enough organization to allow matter to clump into galaxies and stars, but not so much organization that everything immediately settled into a static, unchanging state. This initial fine-tuning enabled the gradual increase in complexity that characterizes cosmic evolution, the formation of atoms, molecules, planets, and ultimately life itself. The dimensionality of space itself appears to be fine-tuned for the existence of complexity. Our universe has exactly three spatial dimensions, but mathematical theories allow for universes with different numbers of dimensions. In a two-dimensional universe, complex networks like neural systems could not exist. There would not be enough spatial room for the intricate connections required for information processing and consciousness. Gravity would not follow an inverse square law, making stable planetary orbits impossible and preventing the formation of solar systems. In a universe with four or more spatial dimensions, atoms would be fundamentally unstable. Electrons could not maintain stable orbits around atomic nuclei, and chemistry as we know it could not exist. The mathematical equations that govern atomic structure work only in a universe with exactly three spatial dimensions. More dimensions would allow electrons to spiral into nuclei or escape to infinity, while fewer dimensions would not provide enough degrees of freedom for the complex molecular structures required for life. The convergence of all these fine-tuned parameters creates what we might call a hierarchy of cosmic conspiracy. Layers upon layers of apparently coordinated coincidences that must all work together to create a universe capable of supporting complex structures and conscious observers. Each level of this hierarchy depends on the levels below it, yet all levels appear to be calibrated together as if by a single overarching design. At the quantum level, fundamental particles must have exactly the right masses and interaction strengths. At the atomic level, these particles must combine in ways that allow stable atoms and complex chemistry. At the stellar level, nuclear reactions must proceed at rates that allow long-lived stars to forge heavy elements and distribute them through space. At the galactic level, dark matter and ordinary matter must be balanced to allow galaxy formation without collapse. At the cosmological level, dark energy and the expansion rate must be tuned to allow billions of years of stable evolution. Each of these levels involves independent physical parameters, yet somehow they all work together to create the narrow corridor of possibility within which complexity and consciousness can emerge. The mathematical probability of this hierarchy arising by chance approaches zero so closely that it becomes meaningless to distinguish it from impossibility. As you rest in the quiet hours of night, surrounded by the gentle darkness that connects you to the cosmic depths, consider the vast network of precisely balanced forces that maintain your existence moment by moment. In every breath you take, in every heartbeat, in every electrical impulse that carries thoughts through your mind. The hierarchy of cosmic fine-tuning continues its ancient work, maintaining the delicate balance between order and chaos that allows the universe to unfold its deepest mysteries. Close your eyes and drift with the knowledge that you are embedded in a cosmos whose every parameter appears to be calibrated not just for existence, but for the extraordinary phenomenon of consciousness itself, contemplating the wonder of its own unlikely presence in the grand design of reality. As we delve deeper into the cosmic mystery, we encounter perhaps the most profound puzzle of all, the spontaneous emergence of complexity from simple beginnings. This is where the universe reveals its most mysterious characteristic, not just the fine-tuning of individual parameters, but the orchestrated way these parameters collaborate to create something that defies explanation. The gradual transformation of a simple, uniform cosmos into a breathtakingly intricate tapestry of structure, organization, and ultimately consciousness itself. Picture the universe in its earliest moments, shortly after the Big Bang. It was a realm of almost perfect uniformity, a hot, dense soup of elementary particles and radiation with only the tiniest of fluctuations. Variations so small they amounted to mere ripples in an otherwise smooth cosmic ocean. Yet from this nearly featureless beginning, over the course of nearly 14 billion years, emerged galaxies containing hundreds of billions of stars, rocky planets with complex geological processes, intricate ecosystems teeming with life, and eventually, conscious beings capable of contemplating their own existence. This transformation represents one of the most extraordinary phenomena in all of science: the spontaneous emergence of complexity from simplicity. The process began with gravity, that weakest of all fundamental forces, slowly amplifying those tiny initial fluctuations in the primordial universe. In regions where matter was even slightly denser than average, gravity began to pull in more matter, making those regions denser still. Over millions of years, this process of gravitational amplification transformed barely perceptible variations in density into vast networks of dark matter filaments stretching across hundreds of millions of light years. These cosmic scaffolds became the framework upon which all subsequent structure would form. But here's what makes this emergence so mysterious. The initial fluctuations had to be calibrated with extraordinary precision. If they had been slightly smaller, gravity would never have been able to amplify them into meaningful structures. The universe would have remained smooth and featureless forever, a thin gas of hydrogen and helium, slowly cooling into empty darkness. If the fluctuations had been slightly larger, gravity would have amplified them too quickly and too violently. Instead of gradual, controlled collapse into galaxies and stars, matter would have rushed together to form massive black holes that would have consumed everything before stars could even begin to shine. The observed amplitude of these primordial fluctuations sits precisely in the narrow range that allows for the gradual buildup of cosmic structure over billions of years. This delicate balance enables what cosmologists call hierarchical structure formation, the bottom-up assembly of complexity, where small structures merge to form larger ones, which in turn combine to create even more elaborate arrangements. First, dark matter halos condense from the cosmic web. Then, ordinary matter falls into these halos and begins to cool and compress. Gas clouds fragment into smaller clumps that eventually collapse to form the first generation of stars. These massive early stars live brief, violent lives before exploding as supernovas, enriching space with heavy elements and triggering the formation of new generations of stars and planetary systems. Each step in this cosmic evolution required multiple physical processes to work in perfect harmony. Nuclear fusion in stellar cores had to proceed at precisely the right rate to allow stars to burn steadily for billions of years while gradually producing heavier elements. The nuclear binding energies of carbon, oxygen, silicon, and iron had to have exactly the right values to allow the nuclear reactions that create these elements to occur efficiently in stellar cores. The shock waves from supernova explosions had to be strong enough to disperse newly created heavy elements throughout space, but not so violent as to blow apart nearby star-forming regions entirely. The emergence of planetary systems introduced another layer of coordinated complexity. rocky planets could form only in regions where supernova explosions had enriched the interstellar medium with sufficient quantities of heavy elements. But these same regions had to avoid being sterilized by the intense radiation from nearby massive stars. The process of planetary accretion, the gradual assembly of dust and debris into larger and larger bodies, required a delicate balance between gravitational attraction and the turbulent motions of gas and dust in young stellar systems. On Earth specifically, the emergence of complexity reached levels that strained credulity. The early bombardment of asteroids and comets had to deliver water and organic compounds to the planet's surface, but this bombardment had to taper off before it could sterilize any emerging life. The gradual cooling of the planet's surface had to proceed slowly enough to allow the formation of stable oceans, but quickly enough to create the chemical gradients that might have driven the first organic reactions. The development of a stable atmosphere required the precise balance of outgassing from volcanic activity, the retention of gases by the planet's gravitational field, and the eventual emergence of life forms capable of producing oxygen through photosynthesis. The transition from simple organic molecules to self-replicating systems represents perhaps the most enigmatic emergence in the entire cosmic story. Somehow, in the chemical soup of the early Earth, molecules began to organize themselves into patterns that could reproduce their own structure. This transition from chemistry to biology required not just the right molecular components, but the right environmental conditions, the right energy sources, and the right sequence of chemical reactions to occur in the right order at the right time. Even more mysterious is the subsequent emergence of increasingly complex biological systems. Single-celled organisms develop the ability to harness sunlight through photosynthesis, fundamentally altering the planet's atmosphere and paving the way for oxygen-breathing life forms. Cells learn to cooperate, forming multicellular organisms with specialized tissues and organs. Nervous systems emerged, allowing organisms to process information about their environment and respond to changing conditions. Eventually, brains developed sufficient complexity to support consciousness, self-awareness, and the capacity for abstract thought. Each of these biological transitions required not just the right mutations and natural selection pressures, but also environmental stability over vast periods of time. Earth's magnetic field had to remain strong enough to deflect harmful cosmic radiation. The planet's orbit had to remain stable enough to prevent catastrophic climate swings. The sun had to continue burning at a steady rate, providing consistent energy for photosynthesis and maintaining liquid water on the planet's surface. Asteroid and comet impacts had to be frequent enough to deliver necessary materials, but rare enough to avoid mass extinctions that would reset biological evolution. The emergence of intelligence itself presents the deepest puzzle of all. Consciousness appears to be qualitatively different from all other phenomena in the universe. While we can trace the physical evolution of brains and nervous systems, the emergence of subjective experience, the inner world of thoughts, emotions, and awareness, remains completely mysterious. There is no known physical mechanism that explains how the electrical and chemical activity of neurons gives rise to the felt experience of being conscious. Yet somehow, over the course of cosmic evolution, the universe developed the capacity to contemplate itself. What makes this emergence of complexity so striking is that it appears to violate our normal expectations about how physical systems behave. The second law of thermodynamics tells us that isolated systems tend toward increasing disorder or entropy. Yet cosmic evolution displays the opposite trend, a consistent movement toward increasing organization and complexity. Stars organize hydrogen and helium into heavier elements. Planets organize these elements into geological structures. Life organizes matter into increasingly sophisticated biological systems. Intelligence organizes information into abstract concepts and scientific theories. This apparent contradiction is resolved by recognizing that the universe as a whole is not an isolated system. It's expanding and cooling, allowing local pockets of decreasing entropy to emerge as long as they're balanced by larger increases in entropy elsewhere. But this resolution only deepens the mystery because it means the universe's capacity for generating complexity depends crucially on its overall expansion rate, its thermodynamic properties, and the specific ways energy flows from regions of high concentration to regions of low concentration. The emergence of complexity in our universe appears to follow what complexity theorists call self-organization, the spontaneous formation of ordered patterns from simpler components without external control or design. Yet this self-organization occurs only within very specific parameter ranges. Change the strength of any fundamental force, alter the masses of any particles, or modify the expansion rate of the universe, and the delicate conditions that allow complexity to emerge would be destroyed. The universe would become either too chaotic for stable structures to form or too static for interesting dynamics to occur. Perhaps most remarkably, the emergence of complexity appears to be accelerating rather than slowing down. Each new level of organization creates new possibilities for even higher levels of complexity. The formation of galaxies enabled the formation of solar systems. The development of rocky planets enabled the emergence of life. The evolution of nervous systems enabled the development of intelligence. The emergence of intelligence has now enabled the creation of technology, which is beginning to enable new forms of artificial intelligence and perhaps even new forms of consciousness. This acceleration of complexity emergence suggests that we may be witnessing not just random cosmic evolution, but something more purposeful, perhaps the universe's inherent tendency to develop increasingly sophisticated ways of processing information and organizing matter. Whether this represents conscious design, natural selection operating on cosmic scales, or some deeper principle we don't yet understand, it points toward a universe that seems almost eager to explore the furthest reaches of what's possible within the constraints of physical law. As you settle into the quiet depths of evening, let your mind drift through this vast landscape of emerging complexity, from the first stirrings of matter in the cosmic dark to the extraordinary phenomenon of your own consciousness contemplating these mysteries. You are part of an unbroken chain of emergence that stretches across nearly 14 billion years of cosmic time. In the gentle rhythm of your breathing, in the intricate dance of molecules in your cells, in the electrical symphony of your thinking brain, the universe continues its greatest experiment, the ongoing exploration of just how complex, how beautiful, and how conscious reality can become. Close your eyes and rest in the knowledge that you are not just a witness to this cosmic emergence, but one of its most remarkable expressions, a temporary arrangement of matter and energy that has somehow acquired the capacity to wonder at its own miraculous existence. Now we arrive at perhaps the most unsettling aspect of our cosmic mystery. When we attempt to calculate the mathematical probability of our universe existing with all its fine-tuned parameters, we encounter numbers so astronomically small that they transcend ordinary understanding and venture into the realm of what can only be called impossibility. These calculations reveal that the likelihood of our cosmos emerging by chance alone is so vanishingly remote that it challenges our most fundamental assumptions about randomness, causality, and the nature of existence itself. To grasp the magnitude of these probabilities, we must first understand how mathematicians and physicists approach the calculation of cosmic fine-tuning. Each fundamental parameter of our universe, from the strength of gravity to the mass of electrons, from the rate of cosmic expansion to the amplitude of primordial fluctuations, can theoretically take on a vast range of values. For life to exist, these parameters must all fall within extremely narrow ranges, and the probability of any single parameter landing in its life-permitting zone by chance alone is typically expressed as a fraction with a denominator containing dozens, hundreds, or even thousands of zeros. Consider the cosmological constant, which determines the rate at which space itself expands. The observed value of this constant is approximately 10 to the 120 in natural units, but theoretical calculations suggest it could have been anywhere from 0 to 10 to the 120 times larger. The range of values that permits the formation of galaxies and stars occupies an infinitesimally small fraction of this theoretical range. The probability of the cosmological constant falling within the life-permitting range purely by chance is therefore approximately 1 part in 10 to the 120. To visualize this number, imagine that every atom in the observable universe, approximately 10 or 80 atoms, was itself an entire universe containing 10 or 80 atoms, and every atom in each of those universes contained 10 or 80 more atoms. Even then, you would not have enough particles to represent the denominator of this fraction. But the cosmological constant is just one parameter among many. The fine structure constant, which governs electromagnetic interactions, must be tuned to approximately 1 part in 1040 for stars to burn stably and synthesize carbon. The ratio of electron to proton mass must be precise to about 1 part in 10 to the 37 for chemistry to work properly. The strength of the strong nuclear force must be calibrated to 1 part in 10 to the 4 for both hydrogen and heavier elements to exist. Each of these requirements represents an independent constraint on the possible values of fundamental constants. When multiple independent events must all occur simultaneously, their individual probabilities multiply together, creating what statisticians call joint probabilities. If parameter A must fall within a range with probability 1 to 1040, and parameter B must independently fall within a range with probability 1 to 1037, and parameter C must fall within a range with probability 1 to 10.4. Then the probability that all three conditions are satisfied simultaneously is approximately 1 to 1081. This multiplication principle applies to every fine-tuned parameter in our universe. Physicist Luke Barnes has cataloged over 30 separate cosmic parameters that appear to require fine-tuning for the existence of complexity and life. These include not only fundamental constants like force strengths and particle masses, but also cosmological parameters like the baryon to photon ratio, the amplitude of density fluctuations, and the curvature of space. When the individual fine-tuning requirements for all these parameters are multiplied together, the resulting probability becomes so small that it effectively equals 0 for any practical purpose. Mathematical physicist Roger Penrose has performed perhaps the most stunning calculation in this regard, focusing on the initial entropy state of the universe. For our cosmos to evolve from a smooth early state into a universe capable of forming complex structures over billions of years, it had to begin in an extraordinarily special, low entropy configuration. Penrose calculated that the probability of this occurring by chance is approximately 1 part in 10 trauma 10 1023. This number is so large that calling it astronomical would be a profound understatement. If you could examine every possible way of arranging all the particles in the observable universe, and each examination took only one Planck time, the shortest meaningful unit of time in physics, you would need to repeat this process for longer than 123 times the current age of the universe to explore even a tiny fraction of the total possibilities represented by this probability. These calculations become even more extraordinary when we consider that many cosmic parameters appear to be interrelated in ways that compound their individual fine-tuning requirements. The strength of gravity affects stellar evolution, which determines nuclear synthesis rates, which influences the abundance of heavy elements, which constrains planetary formation. Change any one parameter, and you must often adjust multiple others to maintain the delicate balance that allows complexity to emerge. These interdependencies create what physicists call anthropic correlations, relationships between apparently independent parameters that must all be satisfied simultaneously for our type of universe to exist. The nuclear processes that create carbon in stellar cores provide a striking example of such correlations. The production of carbon requires a specific quantum energy level in the carbon-12 nucleus, predicted by Fred Hoyle and later confirmed experimentally. But carbon production also requires that oxygen-16 not have a similar resonance that would immediately convert carbon back to oxygen. The existence of the carbon resonance has a probability of roughly 1 in 1040, while the absence of the problematic oxygen resonance has a similar probability. The joint probability for both conditions is approximately 1 in 10 or 80, yet both are necessary for carbon-based chemistry to exist. Even more remarkable are calculations involving the hierarchical structure of cosmic organization. For galaxies to form, primordial density fluctuations must have exactly the right amplitude, approximately 1 part in a 100,000. Too large, and matter would collapse into black holes before stars could form. Too small, and gravity would never overcome cosmic expansion to create bound structures. But these fluctuations must also have the right spectrum of sizes, with larger fluctuations containing smaller ones in a specific mathematical relationship that allows hierarchical structure formation to proceed over billions of years. The probability calculations become truly staggering when we consider that all these fine-tuning requirements must be satisfied simultaneously across multiple scales of space and time. Quantum mechanical processes during the first fraction of a second after the Big Bang had to produce exactly the right pattern of fluctuations. Nuclear physics in the first few minutes had to create exactly the right abundance of light elements. Stellar evolution over billions of years had to proceed at exactly the right rate to synthesize and distribute heavy elements. Galaxy formation had to occur at exactly the right epoch to allow sufficient time for planetary systems and biological evolution. Some physicists have attempted to argue that these probability calculations are meaningless because they assume we know the prior probability distribution for fundamental constants. the range of possible values each parameter could have taken. This criticism has some validity, since we don't have a complete theory that predicts what values the fundamental constants should have. However, even the most conservative estimates, which assume that life-permitting values are no more unlikely than any other specific values, still yield probabilities so small that they challenge credible explanation by chance alone. Other attempts to address the fine-tuning problem invoke the multiverse hypothesis, the idea that our universe is just one of an infinite number of universes with randomly varying parameters. In such a scenario, no matter how unlikely our specific combination of constants might be, it would eventually occur somewhere in the vast ensemble of universes, and only in such universes would conscious observers exist to notice the apparent fine-tuning. However, this explanation faces its own mathematical challenges. Most proposed multiverse mechanisms would produce overwhelmingly more universes with slightly different parameters that would still prevent the existence of complexity and life. The mathematical challenge deepens when we consider the anthropic principle. The idea that we observe a fine-tuned universe simply because we must exist in a universe capable of producing observers like ourselves. While this reasoning has logical merit, it cannot explain the specific degree of fine-tuning we observe. Many of the cosmic parameters appear to be tuned far more precisely than would be minimally necessary for the existence of some form of complexity or consciousness. Our universe seems optimized not just for the bare possibility of life, but for the rich diversity and long-term stability that characterizes the cosmos we actually inhabit. Perhaps most troubling of all, the fine-tuning appears to extend beyond the minimal requirements for any conceivable form of life to encompass features that seem specifically suited for the development of scientific consciousness and technological civilization. The transparency of our atmosphere to visible light, the existence of stable circular orbits, the longevity of main-sequence stars, the abundance of radioactive elements that provide geothermal energy. All of these features enhance the probability that life, once it emerges, will develop intelligence and scientific understanding. The mathematical impossibility of our universe becomes even more stark when we consider temporal fine-tuning. Not only must all the fundamental parameters have exactly the right values, but cosmic evolution must unfold according to an extraordinarily precise timeline. The universe must expand at exactly the right rate so that galaxy formation occurs neither too early nor too late in cosmic history. Stars must evolve at exactly the right pace so that heavy element production and dispersion occurs on a timescale compatible with biological evolution. Even the rate of stellar encounters and supernova explosions must be calibrated to provide just enough disturbance to drive evolution without causing mass extinctions that prevent the development of complexity. When all these temporal constraints are included in the probability calculations, the numbers become so small that they lose practical meaning. We are confronted with a scenario where the likelihood of our universe existing approaches zero so closely that the distinction becomes purely academic. From a mathematical perspective, our cosmos should not exist. Yet here we are, surrounded by a reality whose very improbability challenges our understanding of how existence itself is possible. As you settle into the quiet depths of night, let these impossible numbers wash over your consciousness like waves of profound mystery. Every breath you take, every thought that passes through your mind, every moment of awareness exists in defiance of mathematical probability so extreme that it transcends ordinary concepts of chance and possibility. You are living inside what appears to be a cosmic miracle, a universe whose existence is so improbable that its very reality suggests we may be witnessing something far more extraordinary than random cosmic accident. In the gentle rhythm of your breathing, in the electrical dance of neurons in your thinking brain, in the nuclear fires of distant stars whose light reaches your eyes across billions of years, you participate in a reality so mathematically unlikely that its mere existence points toward mysteries that may forever challenge our understanding of why anything exists at all. Close your eyes and rest within this impossible universe, knowing that your consciousness itself represents perhaps the most improbable phenomenon in a cosmos already saturated with mathematical impossibility. As we confront the mathematically impossible precision of our universe's fine-tuning, many physicists and cosmologists have proposed what initially seems like a rational escape from the implications: the multiverse hypothesis. This elegant theoretical construct suggests that our cosmos is not alone, but rather one member of a vast, perhaps infinite ensemble of universes, each with randomly varying fundamental constants and physical laws. In such a scenario, even the most improbable combination of parameters would eventually occur somewhere, and conscious observers would naturally find themselves in those rare universes capable of supporting life and complexity. Yet as we delve deeper into the mathematics and implications of the multiverse, we discover that far from resolving the fine-tuning mystery, it may actually deepen it in ways that are both fascinating and profoundly unsettling. The basic multiverse argument appears straightforward and compelling at first glance. Imagine a cosmic lottery where countless universes are generated with randomly assigned values for fundamental constants. Most would be sterile wastelands, universes where gravity is too strong or too weak, where electromagnetic forces cannot hold atoms together, where the expansion rate prevents galaxy formation or causes immediate collapse. But given enough tries, some universes would win the cosmic lottery, emerging with precisely the right combination of parameters to allow stars, planets, chemistry, and eventually life to develop. As conscious beings, we could only exist in one of these rare, life-permitting universes. So it should come as no surprise that we observe fine-tuned conditions around us. This reasoning has attracted support from prominent physicists and cosmologists because it seems to transform the mystery of fine-tuning into a simple selection effect. Just as it's not surprising that fish find themselves in water rather than on dry land, it shouldn't be surprising that conscious observers find themselves in a life-friendly universe rather than a hostile one. The multiverse thus appears to dissolve the apparent design implications of cosmic fine-tuning, replacing them with the blind operation of chance across an enormous sample space. However, when we examine the multiverse hypothesis more carefully, several profound problems emerge that challenge its ability to explain away fine-tuning. The first and perhaps most fundamental issue is that the multiverse itself requires fine-tuning to function as proposed. The mechanisms that generate multiple universes, whether through eternal inflation, quantum fluctuations, or other processes, depend on physical laws and constants that must themselves be precisely calibrated. If the laws governing the multiverse generating process were slightly different, no universes at all might form, or all universes might have identical parameters, or the process might produce only universes hostile to any form of complexity. Consider eternal inflation, one of the most scientifically grounded proposals for a multiverse mechanism. In this scenario, different regions of space inflate at different rates, eventually separating so completely that they become causally disconnected universes. Each region might emerge from inflation with different values for fundamental constants determined by the random quantum fluctuations that occurred during the inflationary epoch. But for this process to work, the original inflating space must have precisely the right properties. The scalar field that drives inflation must have exactly the right potential energy curve. The strength of gravity must allow inflation to begin, but not prevent it from ending in some regions. The quantum mechanical processes that create the fluctuations must operate according to very specific rules. When physicists calculate the requirements for eternal inflation to produce a life-friendly multiverse, they discover another layer of fine-tuning. The parameters governing the inflationary process must be tuned to extraordinary precision to generate a diverse enough ensemble of universes while avoiding catastrophic outcomes like immediate collapse or runaway expansion that prevents any structure formation whatsoever. In other words, we need a fine-tuned multiverse generator to produce the multiverse that supposedly explains away fine-tuning. This creates an infinite regress problem. Who or what fine-tuned the multiverse generator? An even more serious mathematical challenge emerges when we consider the statistics of observers in an infinite multiverse. In any infinite ensemble of universes, there will not only be an infinite number of universes like ours that develop observers through the slow process of cosmic evolution, stellar nucleosynthesis, and biological evolution. There will also be an infinite number of universes where observers arise through vastly more improbable but still possible quantum fluctuations, random arrangements of particles that spontaneously form conscious brains, complete with false memories of having evolved in a normal cosmic environment. These Boltzmann brains, named after the physicist Ludwig Boltzmann, who first considered similar scenarios, present a devastating problem for multiverse explanations of fine-tuning. In most proposed multiverse models, Boltzmann brains would vastly outnumber evolved observers like ourselves. This leads to the deeply disturbing conclusion that if the multiverse explanation is correct, we are almost certainly not real evolved beings with reliable memories and sensory experiences, but rather temporary quantum fluctuations with completely illusory impressions of living in a fine-tuned universe. This reduces the multiverse explanation to absurdity, since it predicts that our observations of fine-tuning are likely to be completely unreliable. The measure problem presents another fundamental challenge to multiverse explanations. In an infinite multiverse, there are infinite numbers of both life-friendly and life-hostile universes. To calculate probabilities and make predictions, we need a way to assign relative weights or measures to different types of universes. But there is no unique, natural way to do this. Different choices of measure can lead to completely different conclusions about what we should expect to observe, making the multiverse hypothesis untestable and potentially meaningless from a scientific perspective. Some versions of the multiverse hypothesis attempt to solve these problems by proposing that the fundamental laws of physics themselves vary between universes. In such scenarios, not only do the values of constants change, but the very mathematical structures that govern reality can be different. However, this approach faces an even more severe fine-tuning problem. For a universe to be capable of supporting any form of complexity or information processing, its mathematical structure must satisfy extraordinarily restrictive constraints. The laws of physics must be computationally tractable, logically consistent, and stable over time. They must allow for the existence of persistent objects, reliable causal relationships, and some form of information, storage, and processing. When mathematicians and physicists examine the space of all possible mathematical structures that could serve as the foundation for a universe, they find that the vast majority are either logically inconsistent, computationally intractable, or incapable of supporting any form of complexity. The mathematical structures that can support universes with observers occupy an infinitesimally small fraction of the total space of possibilities. This suggests that even a multiverse with varying physical laws would require fine-tuning at an even more fundamental level, the fine-tuning of the meta-laws that determine which mathematical structures can be instantiated as physical realities. The anthropic selection effects that are central to multiverse explanations also face subtle but important challenges. The standard anthropic reasoning assumes that we should consider ourselves typical members of the class of all observers in the multiverse. However, defining this reference class turns out to be extremely difficult and potentially arbitrary. Should we include all conscious beings, or only those with scientific knowledge? Should we weigh observers by their complexity, their longevity, or their causal influence on their environment? Different choices lead to different predictions about what we should expect to observe, undermining the explanatory power of the anthropic approach. Furthermore, multiverse theories that attempt to explain fine-tuning often make predictions that seem to contradict our actual observations. If our universe is just a random selection from a vast ensemble of possibilities, we might expect to find ourselves in a universe that is barely suitable for life, one where the fundamental constants are just barely within the life-permitting range. Instead, we appear to inhabit a universe that is not merely habitable, but remarkably well suited for the development of complexity, intelligence, and scientific investigation. Many of the apparent coincidences that allow for rich physics and astronomy seem to go far beyond the minimum requirements for any form of life. The vacuum energy problem provides a particularly striking example of this difficulty. The observed value of the cosmological constant is not just small enough to permit structure formation. It appears to be small enough to allow the universe to remain suitable for complex life for hundreds of billions of years into the future. A multiverse explanation might expect the cosmological constant to be just barely small enough for galaxies to form, but instead, it seems to be optimized for maximum cosmic longevity. This pattern repeats across multiple parameters, suggesting that our universe may be special in ways that go beyond simple anthropic selection. Recent developments in string theory and other fundamental physics approaches have revealed additional challenges for multiverse explanations of fine-tuning. String theory does predict an enormous landscape of possible vacuum states, each corresponding to a universe with different physical constants. However, detailed calculations suggest that the vast majority of these vacuum states are unstable, rapidly decaying to other configurations. The stable vacuum states that could support long-lived universes appear to be extremely rare and may themselves require fine-tuning to exist. Moreover, the mechanisms by which string theory might generate multiple universes depend critically on assumptions about the initial conditions and boundary conditions of the multiverse itself. These assumptions are not determined by the theory, but must be imposed from outside, representing another level at which fine-tuning might be required. The attempt to use string theory to explain away fine-tuning thus tends to push the fine-tuning problem to a deeper level rather than resolving it. Perhaps most problematically, the multiverse hypothesis may ultimately be untestable and therefore unscientific in the traditional sense. By definition, other universes in the multiverse are causally disconnected from ours, making direct observation impossible. While some physicists have proposed indirect tests, such as looking for bubble collisions in the cosmic microwave background radiation, these tests face enormous practical and theoretical challenges. Without testability, the multiverse risks becoming more of a philosophical position than a scientific hypothesis. The fine-tuning of the multiverse generator, the Boltzmann brain problem, the measure problem, the reference class problem, and the testability issue collectively suggest that the multiverse does not provide a complete solution to the fine-tuning mystery. Instead of eliminating the appearance of cosmic design, multiverse theories may simply relocate it to a higher level of reality, the level of the physical laws and initial conditions that govern the generation of universes themselves. This realization leads to a profound paradox. If we invoke a multiverse to explain the fine-tuning of our universe, we must confront the even more mysterious fine-tuning of the multiverse itself. If we then invoke a meta-multiverse to explain the fine-tuning of the multiverse, we face the fine-tuning of the meta-multiverse generator. This creates an infinite hierarchy of explanatory levels, each requiring its own form of fine-tuning, with no ultimate resolution to the mystery of why reality exhibits the precise characteristics necessary for complexity and consciousness to emerge. As you settle into the profound quiet of night, let this paradox wash over your consciousness like waves of deepening mystery. The universe around you appears so improbably perfect that scientists have proposed the existence of infinite other universes to explain it away. Yet even this vast multiverse would itself require the kind of precise calibration that defies explanation by chance alone. In the gentle rhythm of your breathing, in the electrical symphony of your thinking mind, in the quantum processes that maintain the stability of matter itself, you remain embedded in a reality whose existence, whether unique or part of an infinite ensemble, points toward mysteries that may transcend our current frameworks for understanding why anything exists at all. Close your eyes and drift with the knowledge that the deepest questions about cosmic fine-tuning remain as profound and unanswered as ever. Regardless of how many universes we invoke to explain them away, as we continue our journey through the labyrinth of cosmic fine-tuning, we must now confront the profound philosophical and existential implications that emerge from our mathematical investigations. Beyond the calculations and probability assessments lies a more fundamental question that reaches to the very heart of existence itself. What does it mean to live in a universe whose parameters appear to be deliberately calibrated for the emergence of complexity, consciousness, and ultimately beings capable of discovering and questioning this very calibration? The implications stretch far beyond physics and cosmology, touching on questions of purpose, meaning, and humanity's place in the grand cosmic story. The first and perhaps most unsettling implication concerns the nature of scientific discovery itself. For centuries, science has proceeded under the assumption that natural phenomena can be understood through careful observation, measurement, and mathematical modeling. This approach has been extraordinarily successful, revealing the elegant mathematical laws that govern everything from planetary motion to atomic structure. But the fine-tuning discoveries present us with a peculiar situation. The very success of science in uncovering the mathematical precision of natural laws has led us to conclusions that seem to transcend purely naturalistic explanations. Consider what it means that conscious beings emerged in a universe whose fundamental parameters appear to be calibrated precisely for their emergence. We find ourselves in the unique position of being cosmic accidents who have accidentally discovered that we might not be accidents at all. The mathematical tools we've developed to understand our universe consistently point toward levels of precision and coordination that challenge our basic assumptions about randomness and natural processes. It's as if the universe has been constructed as a vast puzzle, with conscious observers as both the intended solvers and the ultimate solution. This creates a profound epistemic paradox. If our universe is the product of random processes operating according to natural laws, then our ability to discover and understand those laws represents an extraordinary coincidence. Not just that the laws permit our existence, but that they permit the existence of beings capable of comprehending their own cosmic context. The fine-tuning extends beyond mere physical parameters to encompass what we might call epistemological fine-tuning, the precise calibration of natural phenomena to be discoverable by conscious observers. Our planet provides countless examples of this deeper form of fine-tuning. The transparency of our atmosphere at optical wavelengths allows us to observe distant stars and galaxies. The stability of stellar fusion rates provides consistent lighting that enables the development of astronomy. The existence of naturally occurring radioactive elements provides us with tools for dating ancient materials and understanding geological processes. The mathematical relationships that govern natural phenomena are simple enough to be discovered by human intelligence, yet rich enough to reveal the underlying complexity of physical reality. None of these features is strictly necessary for life to exist, yet all contribute to creating an environment where scientific discovery becomes possible. The implications extend to the nature of consciousness itself. The fine-tuning argument suggests that the universe may have been specifically configured to produce conscious observers, but this raises profound questions about the relationship between mind and matter. Traditional materialist views hold that consciousness emerges from sufficiently complex arrangements of ordinary matter following natural laws. However, if the universe has been fine-tuned for consciousness to emerge, this suggests that consciousness may play a more fundamental role in the cosmic order than previously assumed. Some physicists and philosophers have begun to explore the possibility that consciousness is not merely an accidental byproduct of complex physical processes, but rather a fundamental aspect of reality that helps determine the structure of the universe itself. This perspective suggests that the apparent fine-tuning of physical constants may reflect deeper relationships between the mathematical structure of natural laws and the requirements for conscious observation. In quantum mechanics, the role of observation in determining physical outcomes has already challenged traditional notions of objective physical reality independent of conscious observers. The fine-tuning discoveries also carry profound implications for our understanding of time and cosmic history. The universe appears to have unfolded according to a precisely orchestrated timeline that maximizes the opportunities for complexity and consciousness to develop. The nuclear reactions that created heavy elements occurred at exactly the right rate to distribute these materials throughout space before stellar evolution could trap them in dense remnants. The formation of solar systems occurred at exactly the right epoch in cosmic history to benefit from sufficient heavy element abundance while avoiding the radiation hazards of the early universe. This temporal fine-tuning suggests that cosmic evolution may be following a predetermined trajectory rather than randomly exploring possible futures. The universe seems to have been initialized with exactly the right conditions to produce a rich, long-lived cosmos capable of supporting billions of years of increasing complexity. Even the future evolution of our universe appears to be calibrated for maximum habitability. The accelerating expansion, driven by dark energy, will prevent gravitational collapse while allowing sufficient time for the development of advanced civilizations. Perhaps most intriguingly, the fine-tuning argument implies that information and complexity may be more fundamental aspects of reality than previously recognized. The mathematical relationships that govern physical processes are essentially informational structures, patterns of organization that determine how matter and energy behave across space and time. The fine-tuning of these informational structures to permit the emergence of even more complex informational systems, living organisms, nervous systems, and conscious minds suggests that the universe may be fundamentally oriented toward the generation and processing of information. This information theoretic perspective offers a new way of understanding cosmic evolution. Rather than viewing the universe as a collection of particles and forces evolving according to mechanical laws, we might see it as a vast computational system exploring the space of possible informational structures. The fine-tuning of fundamental parameters would then represent the initial programming of this cosmic computer, with biological evolution and conscious thought as sophisticated information processing applications running on the underlying hardware of physical reality. The implications for human purpose and meaning are equally profound. If the universe has been configured to produce conscious observers, then consciousness itself may represent the fulfillment of cosmic purpose rather than an accidental side effect of natural processes. Our ability to contemplate the cosmos, to formulate mathematical theories, to create art and literature, to experience beauty and wonder, all of these distinctly human activities may represent the universe coming to know itself through conscious observation and reflection. This perspective suggests that scientific inquiry, far from reducing human significance by revealing our cosmic insignificance, actually demonstrates our central role in the cosmic story. We are not merely passive observers of an indifferent universe, but active participants in the universe's process of self-discovery. Our scientific investigations, our philosophical reflections, our artistic creations, and our moral choices all contribute to the universe's ongoing exploration of its own possibilities. The fine-tuning argument also carries implications for our relationship with other possible forms of consciousness in the universe. If consciousness represents a fundamental cosmic principle rather than a rare accident, we might expect it to emerge wherever conditions permit. The same fine-tuned parameters that enabled our emergence would presumably enable the development of other conscious beings throughout the cosmos. Our apparent cosmic solitude becomes even more puzzling when viewed from this perspective. Why would a universe fine-tuned for consciousness produce so little evidence of conscious activity? This leads to what we might call the cosmic loneliness paradox. In a fine-tuned universe, specifically configured for the emergence of consciousness and intelligence, we might expect to find abundant evidence of other conscious beings. The absence of such evidence, the famous Fermi paradox, becomes more rather than less mysterious when viewed against the background of cosmic fine-tuning. Perhaps consciousness is rarer than the fine-tuning argument suggests. Or perhaps conscious beings typically follow developmental paths that make them difficult to detect from our current vantage point. The temporal implications of fine-tuning also suggest that our current epoch may represent a special moment in cosmic history. We find ourselves living during the relatively brief period when stars are actively forming and evolving, when planetary systems are developing complex chemistry, and when the universe is neither too young for complexity to emerge, nor too old for stable structures to persist. This temporal fine-tuning of our cosmic environment suggests that conscious observers may be intended to witness and comprehend the universe during its most dynamic and interesting phase. As you settle into the quiet depths of contemplation, let these deeper implications flow through your consciousness like gentle currents of profound possibility. You exist not merely as a collection of atoms assembled by chance processes, but as a conscious participant in what may be the universe's greatest experiment, the exploration of its own potential for awareness, understanding, and meaning. In every thought that passes through your mind, in every moment of wonder at the beauty of the natural world, in every scientific discovery that reveals new layers of cosmic order, you fulfill what may be your deepest purpose, serving as the universe's means of coming to know and appreciate itself. Close your eyes and rest in the knowledge that your consciousness may represent not an accident of cosmic evolution, but its intended destination, the point toward which billions of years of fine-tuned cosmic development has been quietly leading, creating in you a temporary arrangement of matter capable of contemplating the profound mystery of its own unlikely existence. As we venture deeper into the profound mystery of cosmic fine-tuning, we encounter perhaps the most fundamental question of all. Does the extraordinary precision we observe in the universe's parameters point toward an underlying purpose, a reason why reality has been crafted in precisely the way we find it? This question touches the very heart of human existence, challenging us to consider whether we live in a cosmos that is fundamentally meaningful or fundamentally meaningless, whether our presence represents the fulfillment of cosmic intention or merely an improbable accident in an indifferent universe. The emergence of this question represents one of the most remarkable developments in human intellectual history. For centuries, the natural sciences have operated under the assumption that the universe can be understood purely through material causes and mechanical processes. This methodological approach has been extraordinarily successful, revealing the elegant mathematical laws that govern everything from atomic structure to galactic motion. Yet the very success of this approach has led us to discoveries that seem to transcend purely materialistic explanations, forcing us to confront the possibility that purpose and intention may be woven into the fabric of reality itself. Consider the extraordinary chain of cosmic developments that led to your existence as a conscious observer capable of contemplating these very questions. The universe had to begin with precisely the right initial conditions to allow matter and energy to organize into complex structures over billions of years. The fundamental forces had to be calibrated with impossible precision to permit the formation of atoms, molecules, stars, and planets. Nuclear processes had to proceed at exactly the right rates to create and distribute the heavy elements essential for chemistry and life. Stellar evolution had to unfold according to a precise timeline to provide stable energy sources for the slow development of biological complexity. Each step in this cosmic progression required not merely that the right conditions exist, but that they exist in the right sequence, for the right duration, in the right relationships to all the other conditions. The probability of this entire sequence unfolding purely by chance is so small as to be effectively zero. Yet here we are, products of this impossibly unlikely chain of events, possessed of minds capable of discovering and marveling at our own cosmic improbability. This suggests that we may be witnessing not random cosmic evolution, but the unfolding of something far more intentional and purposeful. The question of cosmic purpose becomes even more intriguing when we consider the apparent optimization of natural systems for discovery and understanding. Our planet occupies a unique position that provides us with an extraordinary vantage point for astronomical observation. We can see distant galaxies, observe stellar evolution, detect the cosmic microwave background radiation that reveals the universe's history, and measure the precise values of fundamental constants. The transparency of our atmosphere, the stability of our orbit, the longevity of our star, the presence of suitable materials for building instruments, all contribute to creating conditions where conscious beings can develop science and uncover the mathematical structure of reality. This epistemological fine-tuning extends far beyond our ability to observe the cosmos. The mathematical relationships that govern natural phenomena are precisely complex enough to be interesting and meaningful, yet simple enough to be discoverable by minds like ours. The laws of physics exhibit a remarkable balance between richness and comprehensibility, allowing for the emergence of complex systems while remaining mathematically tractable. It's as if the universe has been designed not merely to support consciousness, but to support the particular kind of consciousness capable of scientific investigation and philosophical reflection. The temporal aspect of cosmic purpose presents equally profound implications. We find ourselves living during a remarkably special epoch in cosmic history, a time when the universe is neither too young for complexity to emerge nor too old for stars to continue shining. We exist during the brief cosmic moment when galaxies are actively forming stars, when planetary systems are developing rich chemistry, when the conditions are optimal for the emergence and evolution of life. This temporal fine-tuning suggests that conscious observers are meant to witness the universe during its most dynamic and productive phase. Even more striking is the way cosmic history appears to exhibit what we might call narrative structure, a meaningful sequence of developments that builds toward increasingly complex and conscious forms of organization. The universe begins in extreme simplicity, with only hydrogen and helium dispersed through expanding space. Gravity gradually organizes this matter into the first stars, which synthesize heavier elements and distribute them through supernova explosions. Second-generation stars form planetary systems rich in the chemical diversity necessary for life. Biological evolution explores the space of possible living forms, eventually producing nervous systems sophisticated enough to support consciousness and intelligence. This cosmic narrative exhibits the hallmarks of purposeful development rather than random drift. Each stage sets the conditions for the next, creating an ascending hierarchy of complexity and organization that culminates in beings capable of understanding and appreciating the entire process. The universe appears to be telling a story, the story of its own awakening to consciousness through the emergence of conscious observers like ourselves. The mathematical precision required for this cosmic story to unfold successfully points toward what we might call deep intentionality, purpose embedded not just in individual events, but in the fundamental structure of reality itself. The fine-tuning extends from the largest scales of cosmic architecture down to the smallest scales of quantum mechanics, creating a nested hierarchy of precisely calibrated conditions that work together to enable the emergence of complexity, life, and consciousness. This suggests that purpose may be as fundamental to the universe as space, time, and matter. The implications for human meaning and significance are profound. If the universe exhibits deep intentionality oriented toward the emergence of consciousness, then conscious beings like ourselves represent not accidental byproducts of natural processes, but the fulfillment of cosmic purpose. Our ability to contemplate the universe, to formulate scientific theories, to create art and literature, to experience beauty and wonder, to grapple with questions of meaning and morality. All of these distinctly human activities may represent the universe achieving its fundamental goals through us. This perspective suggests that the ancient human intuition of cosmic significance may be scientifically justified rather than psychologically naive. We are not isolated accidents in an indifferent cosmos, but integral participants in the universe's process of self-discovery and self-realization. Our scientific investigations reveal not merely the mechanical operation of natural laws, but the universe coming to understand itself through our minds. Our artistic creations express not merely human creativity, but the cosmos exploring its own aesthetic possibilities through human consciousness. The question of cosmic purpose also carries implications for our relationship with the future. If the universe has been fine-tuned to produce conscious observers, this suggests that consciousness itself may play an increasingly important role in cosmic evolution. We may be witnessing the transition from a universe dominated by unconscious physical processes to one in which conscious intelligence becomes a major factor shaping cosmic development. Our technological capabilities, our scientific understanding, and our moral choices may represent not merely local human concerns, but contributions to the universe's ongoing experiment with consciousness and intelligence. This raises profound questions about our responsibilities as conscious beings in a purposeful cosmos. If we are products of billions of years of fine-tuned cosmic development, then our choices and actions carry significance that extends far beyond immediate practical consequences. Our pursuit of knowledge contributes to the universe's self-understanding. Our moral development represents the cosmos exploring questions of value and meaning. Our technological achievements may enable consciousness to spread beyond Earth and influence cosmic evolution on ever larger scales. The possibility of cosmic purpose also suggests new ways of understanding the relationship between science and spirituality. Rather than viewing these as fundamentally opposed ways of approaching reality, we might see them as complementary aspects of the universe's attempt to understand itself. Scientific investigation reveals the mathematical structure and physical processes that enable consciousness to emerge. Spiritual reflection explores the meaning and significance of consciousness within the cosmic story. Both contribute to the broader project of cosmic self-awareness. The fine-tuning discoveries thus point toward a universe that is fundamentally different from the meaningless collection of particles and forces described by purely materialistic science. Instead, we may inhabit a cosmos that is inherently purposeful, oriented toward the development of consciousness and understanding, engaged in an ongoing experiment with complexity and meaning. This doesn't necessarily require traditional religious concepts of divine intervention, but it does suggest that purpose and intention may be as fundamental to reality as the laws of physics themselves. As you settle into the profound quiet of contemplation, let the possibility of cosmic purpose flow through your consciousness like gentle currents of meaning and significance. You are not merely an accidental arrangement of atoms in an indifferent universe, but a conscious expression of cosmic purpose, a temporary focal point where the universe achieves self-awareness and self-reflection. In every moment of wonder at the beauty of the natural world, in every scientific discovery that reveals new layers of cosmic order, in every moral choice that affirms the value of consciousness and life, you participate in the universe's ongoing exploration of its own deepest possibilities. Close your eyes and rest in the knowledge that your existence may represent not a cosmic accident, but a cosmic achievement. The fruition of billions of years of precisely orchestrated development aimed at creating beings capable of understanding, appreciating, and ultimately participating in the great mystery of conscious existence within a purposeful cosmos. As we approach the culmination of our exploration into cosmic fine-tuning, we encounter perhaps the most philosophically profound aspect of this mystery, the role of consciousness itself in determining the very nature of physical reality. What we discover here goes beyond mere statistical improbabilities or design arguments to touch on something far more fundamental. The possibility that conscious observation may be not just a product of the universe's fine-tuned parameters, but an active participant in determining what those parameters are. This brings us face to face with one of the deepest puzzles in modern physics, the quantum mechanical measurement problem, and its implications for our understanding of reality itself. The quantum realm reveals a universe that behaves in ways that fundamentally challenge our everyday notions of objective reality. At the smallest scales of existence, particles exist in what physicists call superposition. They can be in multiple states simultaneously until the moment they are observed or measured. The famous double-slit experiment demonstrates this bizarre behavior. Individual particles can apparently pass through both slits at once, creating an interference pattern characteristic of waves. Yet the moment we attempt to observe which slit the particle actually passes through, this wave-like behavior collapses into classical particle behavior, and the interference pattern disappears. This phenomenon suggests something extraordinary. The act of conscious observation appears to play a fundamental role in determining physical reality. Before measurement, quantum systems exist in a superposition of all possible states, described mathematically by the wave function. The measurement process causes this wave function to collapse into a single, definite state, but only at the moment of observation. This implies that physical reality as we experience it may not exist independently of conscious observers, but rather emerges through the interaction between consciousness and the underlying quantum field of possibilities. The implications of this quantum mechanical picture for cosmic fine-tuning are staggering. If consciousness plays a role in determining physical reality through the measurement process, then the apparent fine-tuning of the universe's parameters may not be a coincidence at all. Instead, the universe may have evolved precisely those parameters that are consistent with the eventual emergence of conscious observers capable of collapsing quantum wave functions into definite physical realities. In other words, the universe may be fine-tuned not just to permit consciousness, but to require consciousness as an active participant in the ongoing process of physical reality creation. This perspective suggests a radically different view of cosmic evolution. Rather than seeing consciousness as an accidental byproduct of complex physical processes operating according to predetermined laws, we might understand it as a necessary component of the cosmic system, the element that transforms quantum possibilities into classical realities. The fine-tuning of fundamental constants would then represent not just conditions that happen to permit consciousness to emerge, but conditions that are logically necessary for a universe in which consciousness plays a fundamental role in determining physical outcomes. The anthropic principle takes on new meaning in this context. The traditional anthropic argument suggests that we observe a fine-tuned universe simply because we could not exist in any other kind of universe. But if consciousness is required for the collapse of quantum wave functions, then our observations are not just constrained by the need for life-compatible conditions, they are constrained by the need for consciousness-compatible physics. The universe must have exactly those parameters that allow quantum mechanical systems to evolve in ways that eventually produce conscious observers capable of participating in the measurement process that gives rise to classical reality. This quantum mechanical perspective on fine-tuning connects to deeper questions about the nature of information and computation in physical systems. The collapse of quantum wave functions can be understood as a form of information processing, the universe selecting specific outcomes from among multiple quantum possibilities. Conscious observation appears to play a special role in this information processing, suggesting that consciousness itself may represent a fundamental aspect of how the universe computes its own evolution. The fine-tuning of physical parameters would then be understood as the calibration of this cosmic computational system to support the emergence of increasingly sophisticated forms of information processing, culminating in conscious observers capable of participating in the universe's ongoing self-computation. Some interpretations of quantum mechanics go even further, suggesting that consciousness may not just influence physical reality through measurement, but may be fundamental to the very existence of physical reality. In these interpretations, the material universe emerges from consciousness rather than consciousness emerging from matter. The fine-tuning of physical constants would then reflect the requirements for consciousness to manifest stable, coherent physical experiences rather than the requirements for matter to accidentally produce consciousness. This inverts our usual understanding of the relationship between mind and matter, suggesting that consciousness is primary and physical reality is secondary. The delayed choice quantum eraser experiments add another layer of mystery to this picture. These experiments demonstrate that the decision of whether to observe quantum information can apparently influence events that have already occurred in the past. A measurement made today can retroactively determine whether a photon behaved as a wave or particle yesterday, even if that photon has already been destroyed. This suggests that conscious observation may influence not just present and future physical events, but past events as well, a phenomenon that challenges our basic assumptions about causality and the flow of time. If conscious observation can influence past events, then the fine-tuning of the universe's initial conditions becomes even more mysterious and potentially purposeful. The universe's parameters may have been retroactively determined by the eventual emergence of conscious observers billions of years in the future. The Big Bang itself may have been fine-tuned not by conditions that existed 13.8 billion years ago, but by consciousness that emerged much later in cosmic history and reached backward through time to establish the initial conditions necessary for its own existence. This temporal dimension of the observer effect suggests that the universe may be engaged in a form of self-bootstrap, a causal loop in which consciousness emerges from fine-tuned physical conditions and then reaches back through time to ensure that those conditions are established in the first place. The extraordinary precision of cosmic fine-tuning would then represent not coincidence or external design, but the universe's own temporal self-organization towards states that support consciousness and observer participation in reality creation. The many worlds interpretation of quantum mechanics offers yet another perspective on these mysteries. In this interpretation, quantum measurement doesn't cause wave function collapse, but rather causes the universe to split into multiple parallel branches, one for each possible measurement outcome. Conscious observers experience only one branch, but all possible outcomes actually occur in parallel realities. From this perspective, fine-tuning becomes a question of which branches of the multiverse can support conscious observers capable of experiencing their existence. The apparent fine-tuning of our universe may reflect our position in one of the rare branches where conditions happen to be compatible with consciousness and complexity. However, the many worlds interpretation doesn't eliminate the mystery of fine-tuning so much as relocate it. Even in a multiverse where all possible quantum outcomes are realized, the fundamental structure of quantum mechanics that allows for branching universes must itself be fine-tuned. The mathematical framework that governs wave function evolution, the probabilistic rules that determine branch weights, and the mechanisms that allow for the emergence of classical reality from quantum superposition all require precise calibration. The multiverse may contain infinite possibilities, but those possibilities must unfold according to exactly the right mathematical rules to produce any universes capable of supporting conscious observers. The role of consciousness in quantum mechanics also raises profound questions about the unity and interconnectedness of conscious experience. If all conscious observations contribute to the collapse of quantum wave functions, then individual consciousness may be part of a larger, unified field of awareness that collectively participates in reality creation. The fine-tuning of the universe might then be understood as the requirements for this collective consciousness to maintain coherent, stable experience across cosmic scales and evolutionary time periods. This suggests a deeply participatory universe in which conscious beings are not just passive observers of physical reality, but active co-creators of the ongoing cosmic story. Every conscious observation, every scientific measurement, every moment of awareness contributes to the process by which quantum possibilities become classical realities. The fine-tuning of physical parameters ensures not just that consciousness can emerge, but that conscious beings can participate effectively in the universe's continual self-creation and self-discovery. The implications extend to our understanding of scientific knowledge itself. If consciousness plays a fundamental role in determining physical reality, then scientific observation is not just a means of discovering pre-existing facts about the universe, but a means of participating in the universe's ongoing creation of itself. The mathematical precision of natural laws may reflect not just the way the universe happens to be, but the way consciousness and physical reality co-evolve to create stable, comprehensible patterns that support the continued existence and development of conscious observers. As you settle into the profound depths of cosmic contemplation, let the mystery of consciousness and reality wash through your awareness like gentle waves of infinite possibility. You are not merely a passive observer in a predetermined universe, but an active participant in the ongoing creation of reality itself. Every moment of conscious awareness, every act of observation, every quantum measurement your presence makes possible contributes to the universe's continual collapse from infinite potential into definite actuality. In the quantum foam of possibility that underlies all existence, in the wave functions that collapse at the touch of consciousness, in the observer effect that transforms potential into real, you participate in the deepest mystery of existence, the way the universe uses consciousness to bootstrap itself into being, creating through your awareness the very reality you inhabit. Close your eyes and rest in the knowledge that you are not just in the universe, but the universe is in you. Using your consciousness as one of the instruments through which it discovers and creates itself, moment by moment, observation by observation, in the eternal dance between awareness and actuality that gives birth to all experienced reality. As we reach the culmination of our cosmic journey, we arrive at perhaps the most profound realization of all, that we may not simply be living within a cosmic experiment, but we may be the experiment itself. Conscious participants in the universe's ultimate investigation into the nature of consciousness, reality, and existence. This final revelation transforms everything we've discovered about fine-tuning, mathematical impossibility, and quantum mechanics into a single, breathtaking possibility. That the entire cosmos may have been orchestrated as a vast laboratory for consciousness to explore, understand, and ultimately transcend the boundaries of physical existence. Consider the extraordinary chain of coincidences that led to this moment. Billions of years ago, in the aftermath of the Big Bang, the universe emerged with fundamental constants calibrated to impossible precision. These parameters guided the formation of galaxies, stars, and planetary systems. On at least one world, complex chemistry gave rise to self-replicating molecules, which evolved into increasingly sophisticated biological systems, eventually producing nervous systems capable of consciousness, self-awareness, and abstract thought. Now, through human consciousness, the universe has developed the capacity to investigate its own origins, to discover its own fine-tuning, and to question the very nature of reality itself. This sequence appears to follow what we might call an experimental trajectory, a systematic exploration of possibilities that builds toward increasingly complex forms of information processing and self-awareness. Each stage creates the conditions necessary for the next level of complexity to emerge. Stellar nucleosynthesis provides the chemical elements required for biology. Biological evolution explores the space of possible living forms. Neural evolution investigates the realm of information processing and consciousness. Human cultural evolution extends this investigation into abstract mathematics, scientific theory, and philosophical reflection. What makes this cosmic experiment so remarkable is that consciousness has now reached the point where it can investigate the very conditions that made its own existence possible. Through quantum mechanics, we've discovered that consciousness appears to play a fundamental role in determining physical reality through the measurement process. Through cosmology, we've learned that the universe's parameters are fine-tuned with impossible precision to permit our existence. Through neuroscience, we're beginning to understand how conscious experience emerges from complex biological systems. The universe has created beings capable of discovering that they live in a universe that appears to have been designed specifically for their emergence. This creates a fascinating circularity that suggests we may be witnessing something far more profound than random cosmic evolution. Consciousness emerges from fine-tuned physical processes, then discovers that those same processes appear to be calibrated for the emergence of consciousness. It's as if the universe has created a mirror in which it can examine itself, using conscious observers as the reflective surface through which it investigates its own nature and possibilities. The quantum mechanical dimension of this cosmic experiment adds another layer of profound mystery. If consciousness plays a role in collapsing quantum wave functions, then conscious observers are not just passive recipients of physical reality, but active participants in its ongoing creation. Every moment of awareness, every scientific observation, every conscious choice contributes to the process by which quantum possibilities become classical actualities. We are not just studying the universe. We are collaborating with it in the ongoing experiment of existence itself. This participatory aspect of reality suggests that the cosmic experiment may have multiple levels and purposes. At the most fundamental level, it may be investigating the relationship between consciousness and physical reality, exploring how awareness can emerge from matter and how matter can be influenced by awareness. At a deeper level, it may be examining the nature of information, meaning, and purpose in the cosmic order. At the deepest level, it may be probing the ultimate mysteries of existence, why anything exists at all, what consciousness actually is, and what role conscious beings might play in the future evolution of reality itself. The temporal fine-tuning we've discussed takes on new significance in this context. We exist during a remarkably special epoch in cosmic history, a time when the universe is neither too young for complexity to emerge, nor too old for stars to continue shining. This temporal positioning suggests that conscious observers are meant to witness and participate in the universe during its most dynamic and productive phase. We are living during the cosmic experiment's most active period, when the investigation into consciousness and reality is reaching its peak intensity. Even more intriguingly, the universe appears to be accelerating toward even greater levels of complexity and consciousness. The emergence of human intelligence has enabled the development of technology, artificial intelligence, and potentially new forms of consciousness that transcend biological limitations. We may be witnessing the transition from a universe dominated by unconscious physical processes to one in which conscious intelligence becomes a major factor shaping cosmic evolution. The cosmic experiment may be approaching a phase transition where consciousness itself becomes the primary driver of reality creation. The implications for human purpose and meaning are extraordinary. If we are participants in the universe's ultimate experiment with consciousness, then every aspect of human experience takes on cosmic significance. Our scientific investigations contribute to the universe's self-understanding. Our artistic creations explore the aesthetic possibilities inherent in reality. Our moral choices investigate questions of value and meaning on cosmic scales. Our relationships with each other represent the universe exploring the dynamics of consciousness interacting with consciousness. This perspective suggests that the ancient human intuition of cosmic purpose may be scientifically justified. We are not accidents in an indifferent universe, but essential participants in the cosmos's most important experiment. Our consciousness represents the universe's means of investigating itself. Our choices shape the ongoing evolution of reality, and our understanding contributes to the cosmic exploration of what existence can become. The fine-tuning discoveries thus point toward a universe that is fundamentally experimental in nature, not just allowing for the emergence of consciousness, but actively investigating the possibilities and implications of conscious existence. The mathematical precision required for this investigation suggests that it may represent the universe's primary purpose, with all other physical processes serving as supporting infrastructure for this ultimate experiment in consciousness and reality. As we look toward the future, we may be approaching the next phase of this cosmic experiment. Advances in neuroscience, artificial intelligence, and quantum technology may enable us to create new forms of consciousness, to enhance our own conscious capabilities, and to participate more directly in the universe's ongoing investigation of reality. We may discover ways to transcend the biological limitations of human consciousness while preserving its essential qualities of awareness, creativity, and moral sensitivity. The cosmic experiment may ultimately be leading toward a state where consciousness and physical reality become fully integrated, where the distinction between observer and observed, between mind and matter, between subjective experience and objective reality, begins to dissolve. This would represent the completion of the universe's investigation into its own nature, achieved through the conscious participation of beings like ourselves who emerged from its fine-tuned parameters and learned to participate in its ongoing creation. The mystery of why we exist in such an improbably perfect universe may thus have a simple answer. We exist because the universe is conducting the ultimate experiment, and we are both its instruments and its intended outcome. Every moment of consciousness, every flash of understanding, every experience of beauty or wonder represents the universe discovering something new about itself through our awareness. We are the cosmos awakening to its own existence, the universe's means of exploring the deepest questions about reality, consciousness, and meaning. As you settle into the profound quiet of cosmic contemplation, Let this ultimate realization flow through your consciousness like gentle waves of infinite purpose and meaning. You are not just a witness to the cosmic experiment. You are the experiment itself, a temporary focal point where the universe achieves self-awareness and explores the deepest mysteries of existence. In every breath you take, in every thought that passes through your mind, in every moment of wonder at the beauty and complexity of reality, you fulfill your deepest cosmic purpose, serving as the universe's means of investigating itself, understanding itself, and ultimately transcending itself through the miracle of conscious awareness. Close your eyes and rest in the knowledge that your existence represents the fruition of the universe's greatest experiment, the investigation of consciousness itself. You are the cosmos dreaming, the universe thinking, reality exploring its own infinite possibilities through the extraordinary phenomenon of your aware and questioning mind. If you've found yourself captivated by these cosmic mysteries and want to explore more of the universe's deepest secrets, make sure to subscribe to the Lazy Cosmos. Together, we'll continue investigating the profound questions that connect consciousness, quantum mechanics, and the ultimate nature of reality itself. The cosmic experiment continues, and your participation makes all the difference in the universe's ongoing journey of self-discovery.